Let's say someone gives you a lottery machine and says, this thing spits out random answers, but trust me, somewhere inside there's a winning ticket. That's how many of past existence proofs in complexity theory work. We know hard functions exist, but finding them explicitly and algorithmically is a totally different story. In this talk, I will describe how we make progress in explicitly constructing such hard objects and how this gives us new circular bonds. Okay, hello everyone. I'm Jingxun. Today I'm going to talk about my paper, Maximum Circular Bonds for Exponential-time author Merlin. This is a joint work with Liang and Jiatu. Okay, let's start the talk with maximum circular bonds. The question of proving circular bonds lies at the heart of complexity theory. Because of the clear structure of first circuits, circular bond is conjectured to be the approach to several central open questions. For example, proving a super polynomial circular bond for NP will imply the breakthrough result P not equals to NP. And proving an exponential circular bond for E, the uniform single exponential time class, will imply de-randomization P equals to BPP. Despite the central importance of this result, our current understanding is quite limited. To quote the textbook, computational complexity, a modern approach, circular bonds are complexity theory's Waterloo. To give a sense of how little we know, the best known circular bond for polynomial time algorithm is only 3.1 n. And this is also the state-of-the-art circular bond for even larger class e to the np. This means that we are still super polynomially far away from the desired goals. And to tackle on this notoriously hard problem, there are two broad approaches. One is try to prove larger and larger lower bounds for a fixed class like E. The other, which is the focus of this paper, is to prove a fixed strong lower bound, namely the maximum possible lower bound for smaller and smaller classes. Okay, so what do I mean by maximum? Well, according to Shannon, almost every n-bit Boolean function requires circuit size around 2 to the n over n, and no function can require more than that. So this is the largest lower bound we can ever hope to prove. The first maximum circular lower bound is proven by Cannon, who showed that sigma 3e does not have 2 to the n over n side circuits. And later on, this result is improved by MVW99 to maximum circular bond of e to the sigma 2. And as a recent breakthrough, CHR24 and Li24 further improved the result to maximum circular bond of S2e, which is a subclass of both sigma 2e and pi 2e. Although S2e is already reasonably small class, it still involves two layers of alternations. So a natural question is, can we prove a maximum circular bond for a sigma 1 type class? And currently, the best known sigma 1 type lower bound is still just 3.1 n. So proving a 2 to the n over n lower bound here would represent a major breakthrough. A promising candidate is AME, which is all the Merlin protocols running in single exponential time. It is a class that contains an E, lies inside e to the sigma 2, but is still incomparable with S2E. Let me now pivot to another area that turns out to be closely connected, that's explicit constructions. Say, many important mathematical objects are known to exist through non-constructive or probabilistic arguments, but we still don't know how to systematically construct them. This includes expanders, Ramsey graphs, Hartree tables, extractors, rigid matrices, and good codes. All of these objects emit a non-constructive proof that only shows the existence of such an object. If this is all we know about these things, then probably the best possible explicit construction we can do is just to the total search, which is pretty slow. And fortunately, like for all of these listed projects, the existence of them is actually a probabilistic proof, which shows the desired object is actually very dense. And we can at least construct such an object by randomized algorithm. To further classify these problems, we formalize the problem as follows. We define a family of desirable objects as a property pi over m bit strings. We assume pi is dense, meaning many such objects exist. Then the task becomes constructing a string in pi on input length n, ideally using as little time and randomness as possible. Depending on the complexity of pi, we can classify explicit construction problem as heating dense p property, heating dense np property, and so on. Say, we can draw a diagram like this. Clearly, constructing prime numbers is to hit dense p property as we have deterministic polynomial time primal test. And constructing Hartree table is to hit dense co-NP property as an easy truth table can be verified given its small circuit at witness. So is rigid matrix. Among all these dense co-NP properties, there's a special subset formed by all the range avoidance type property, where all the bad objects are in the image of a small circuit, and getting a non-output of such a circuit will yield an explicit construction of a good object. It is not hard to see both Hartree table and rigid matrix are actually range avoidance type properties. In this context, the first result is obtained by OS17, which shows an explicit construction for dense p property in half exponential time, where half exponential means a function f such that the second iteration of f is exponential. And this result is improved by the breakthrough result CLORS23, which shows an algorithm to construct dense p property in polynomial time. This is definitely the best we can hope for heating dense p property. And regarding range avoidance type property, there's a long line of recent works on it, and CHR24 and Li24 obtained an explicit construction in S2P. These works suggest that pushing further, say, to co-MP or co-AM constructions would be quite meaningful. And in particular, explicit constructions for dense co-AM property would yield new constructions of hard-truth tables and rigid matrices beyond the current range avoidance techniques. That would be meaningful. And interestingly, these two lines of work, maximum circuit lower bounds and explicit constructions, are deeply connected. Actually, the state-of-the-art maximum circuit lower bound is a corollary of the explicit construction of range avoidance type properties. Why? Because we can view circuit lower bound as uniformly and explicitly constructing hard-truth table. As any uniform algorithm that explicitly output a hard-truth table must also have large circuit complexity. Along these lines of work, it's natural to further ask, can we get sequence 1 type maximum circuit lower bound? And can we get explicit constructions for larger class? And we answer those questions in this work. We obtain a maximum circuit lower bound for AMX and an explicit construction for all dense co-AM properties. And our circuit lower bound is also a corollary of our explicit constructions. Specifically, we show that for any constant epsilon between 0 and 1, the class AMX intersect with co-AMX with certain bits of device has maximum circuit complexity. And moreover, our lower bound holds even if the circuit can access to an oracle in AM intersect with co-AM. For our explicit construction result, we show that for any k greater than 1 and for any dense co-AM property P, there is an Arthur Merlin algorithm runs in quasi-polynomial time, taking sublinear bits of device, output in an n-bit string with property P on infinitely many input length n. Here, we say an AM algorithm output a string in the single value sense. That means the AM algorithm should output a canonical string in any computational path to accept. And technically, our algorithm requires several advice bits. The use of advice bits arises because co-AM properties are not easily verifiable by AM protocols. So even if our algorithm narrows down to a small list of candidates, we still need a few bits of advice to pick up the correct one. Okay, now to wrap up the talk, let me briefly share a bit about the technique behind our result. Of course, in the limited time we have, I can't go into all the technical details, but I want to give you a taste of one of the interesting ideas we use. So one of the technical ingredient of our paper is called iterative win-win argument, which is first introduced by CLORS23 and is further used in CHR24. By using iterative win-win argument, we can bypass the long-standing half-exponential barrier for the standard win-win argument. To illustrate the idea of iterative win-win, we need first to have a win-win argument. Say, a win-win argument between input length n1 and n2 will provide something like this. Say, given an A algorithm that has P at input length n1 in time tn1. win-win argument can provide another AM algorithm that runs in quasi-poly N2 time on input length N1 and runs in Tn1 plus poly N2 time on input length N2 and hits P at either N1 or N2. The usual way to use this is to carefully pick N2 to balance the trade-off and get a better algorithm overall. But there's the catch. The new algorithm's running time is still bottlenecked by the original slow running time Tn1. That's where the iterative win-win argument comes in. By iterative win-win argument, we can show that no matter how slow Tn1 is, we can always get an AM time cost poly N algorithm that hits P infinitely often. The idea of iterative win-win is quite natural. Just as its name suggested, we will consider a sequence of L input lengths N1 through NL, where Ni is quasi-poly in N-1. And we will iteratively consider win-win argument between these input lengths. Say, we start with a slow brute force algorithm at input length N1. We will first take win-win argument between N1 and N2 to make input length to make input length N1 efficient. Then we will take input length between N2 and N3 to further make the running time on input length N2 efficient, and so on. We will keep doing this until we reach a super large NL, which is even larger than exponential in N1. Then the original slow part, the exponential time in N1, which is slow in input length N1, but quite small comparing to the much larger input length NL. So in the end, our algorithm will be efficient in all of the input lengths, and which provides an algorithm that's quasi-poly time and hits at least one of the input lengths N1 through NL as desired. And this completes our proof for iterative win-win, and that's all of my presentation today. Thank you.